people on YouTube! I'm Schoko, and today we're watching how the Demon Core killed a man in 9 days. Let's go watch the video!
It looked like a normal, boring metal ball. Smooth, shiny, and a bit bigger than a grapefruit. It didn't glow, it didn't tick, nothing to give away the danger within. But within the span of a year, it took the lives of 2 men, without either one even touching it. This metal ball held enough power to eliminate an entire city, but neither death involved any explosions. The first man died 3 weeks after dropping a brick. The second died 9 days after the slip of a screwdriver. Different tools, same deadly outcome. And it was all because this ball, which eventually got nicknamed the Demon Core, was made of plutonium.
Plutonium!
To tell the story of this small plutonium ball of death, we also need to talk about a different and perhaps much more famous element just 2 squares over on the periodic table. Because while plutonium technically exists in nature, it's in very tiny amounts. So if you want enough for any kind of practical purpose, you have to start with uranium. Uranium sits in the Earth's crust, just waiting to be dug up and refined for nuclear power or nuclear weapons. But if you have a lump of uranium atoms, you can turn some of them into plutonium atoms by...
Y'all ever wonder how people got the idea to use uranium for weapons and stuff like that? Or were they just like, yes, periodic table, we know it all thanks to figuring out all the elements and things. I mean, there was probably people early on that had to research this stuff and see what it was used for and what type of properties it has in it. And I mean, maybe there's some notes out there for that. There probably is.
By bombarding them with neutrons. It's a multi-step process since you actually need to change the number of protons in an atom's nucleus to turn it into a different element. But we don't need to worry about those details in this video. Just like its predecessor, plutonium is useful because it's fissile, meaning the atoms can be split or fissioned into smaller atoms, releasing a ton of energy in the process. But there are some important differences between the two. While both emit the same kind of radiation, if you have 2 balls of equal mass, one uranium and one plutonium, the plutonium ball will emit more radiation in the same amount of time, making it riskier to handle. And most importantly for our story, it takes less plutonium to reach something called criticality, which is when things get interesting, if not disastrous. We will come back to that in a bit. In the 1940s, the United States' effort to build a nuclear bomb focused on uranium. But even though uranium is present in reasonable quantities in Earth's crust, there's a catch. The isotope of uranium that's fissile is uranium-235. As the name implies, uranium-235 has a combined total of 235 protons and neutrons in its nucleus. But over 99% of all the uranium mined on Earth is uranium-238, which is still radioactive, but not fissile. In other words, 99% of all the uranium we find can't be used for either nuclear energy or nuclear weapons. There's also the problem that these isotopes always come mixed together. So scientists had to develop ways to separate the 235 from the 238 bulk, which is about as easy as trying to differentiate decaf coffee from regular just based on smell. Different isotopes of the same element behave the same chemically, so they are really hard to separate. However, physicists at the University of California, Berkeley discovered that if you bombard those useless uranium-238 atoms with neutrons in a reactor, you get plutonium-239. And plutonium-239 is not only fissile, it can also be easily separated from the uranium. It was a total game changer, and the Manhattan Project shifted gears. They decided to build 2 kinds of bombs. The US dropped one of each on the citizens of Japan, the uranium-powered Little Boy and the plutonium-powered Fat Man. But a second plutonium core had been made, dropped one of each on the citizens of Japan, the uranium-powered...
I didn't realize one was uranium and the other one was plutonium. Yeah, I would understand why the damage was so severe. Hello? Like, oh my goodness. I know, like, the names. are based off of like how much power, but this is insane. I didn't know plutonium was this strong. And the exposure on the innocent people,
powered little boy and the plutonium powered fat man. But a second plutonium core had been made just in case. And when World War II came to a close, it remained at Los Alamos National Laboratory in New Mexico, where scientists could continue their experiments on criticality. This is our demon core. To get into that criticality, we're going to dig into some nuclear physics a bit, but don't worry, we'll keep the metaphors to a maximum. When an atom undergoes fission, it doesn't just crack in half. It also releases a number of lone neutrons that aren't bound to either of the new, smaller nuclei. These neutrons are then free to smash into other atoms, causing them to undergo fission and so on. But whether or not these neutrons will actually do that depends on several factors, like how many atoms you've got altogether and how closely packed those atoms are. If, on average, exactly one neutron from each fissioned atom causes another atom to split, you have what's called a critical reaction. It's like a perfect row of dominoes, where each one knocks over exactly one more. This is an ideal situation for nuclear reactors used to produce energy, a constant, steady stream of reactions that put out a constant amount of energy. Meanwhile, if the neutrons hit fewer than one additional atom, again, on average, the reaction will eventually fizzle out. This is a subcritical reaction. And if more than one neutron from each fission event causes another fission, things can escalate quickly. Now it's like each domino is knocking over 2 or 3 others, spreading exponentially. This is a supercritical reaction. Barring a few experimental exceptions over the decades, this is what you don't want to happen in a nuclear reactor, but you do want to happen in a nuclear bomb. This is also where plutonium gets extra spicy, by which I mean extra dangerous. It releases more neutrons per fission event than uranium does. That means you need less of it in order to go supercritical. But there's more to criticality than just how many atoms there are.
but it really helps because we're getting every little bit of detail and understanding the difference between plutonium, uranium, and how it reacts and what type of reaction you want from the molecules that are, messing with each other as they're either splitting off multiple ways and then doing it multiple times in different directions because of that whole domino type effect. But it's the fact that it can give you different outcomes. So we got the more critical one. I think it was like between critically and just critical. I got that one wrong probably.
It's also about how they're arranged. Imagine we have 100 dominoes in a long line. If one is even a little out of place, the chain can break, stopping the reaction. But if you pack those dominoes into a tight circle, it's much harder to stop the toppling once it starts. The same goes for plutonium atoms. In fact, the core of Fat Man was surrounded on all sides by explosives that detonated inward, compressing the core, increasing the density of the plutonium atoms, and all but guaranteeing a gigantic chain reaction. But what ultimately doomed the men killed experimenting on the demon core was yet another way to help a ball of plutonium hit criticality: neutron reflection. As atoms in the demon core split, some of the neutrons will escape into the surrounding air. It's the end of the road for their nuclear fission dreams. But if you can place something around the core that reflects those neutrons back, you give them another chance. There's no good domino analogy here.
Well, now I understand why learning nuclear stuff in school is... Ooh. Yeah, gotta make sure people are safe.
So let's just say it's like a pinball machine with extra bumpers. This is exactly what our first victim, Harry Daghlian, was doing in 1945.
Oh, wow.
He was trying to reflect neutrons back toward the demon core by surrounding it with bricks made out of tungsten carbide. He was in the lab alone, late at night. too impatient to wait for the morning when his experiment was scheduled to take place. As he added additional bricks around the core, his equipment alerted him that the core was rapidly approaching dangerous territory. He tried to remove his latest brick, but it slipped from his hand before he could clear the assembly. When it fell back down, the extra coverage reflected enough of the core's neutrons to push the deadly orb into a supercritical state. Daglian reacted immediately, shoving the brick to the floor, but the radiation released in just that moment was enough to kill him within weeks. It also irradiated a lone security guard who was stationed a few meters away, but we'll get to his fate later. But before we get to that, we've got to keep the lights on, so here's an ad.
This SciShow video is supported by Brilliant, an interactive online learning platform. Brilliant's app can premium subscription.
Yeah, it not to mention how each particle reacts like an alpha, can't go through clothes. Oh, that's interesting. I didn't know it can't go through clothes.
Now, it's worth noting that the scientists at Los Alamos could have used robots to handle a core like this remotely, but they argued that these robots weren't reliable enough and preferred to do their work by hand to avoid accidents. And yes, they did have certain safety protocols in place, but that doesn't mean they were always followed. Enter Louis Slotin. Instead of the tungsten carbide bricks, Slotin's experiments involved surrounding the demon core with 2 hemispheres of beryllium. Not only is beryllium a neutron reflector, it's also a neutron multiplier. When it gets hit by a neutron, the atoms spit out 2 in return. If tungsten bricks are like extra bumpers in pinball, beryllium is like having extra balls. To increase the amount of reflection, Slotin simply needed to lower the top hemisphere over the core. But instead of resting that hemisphere on the mandatory spacers, so if it slipped out of his hand it wouldn't cover the core too much, he held the 2 halves apart with the end of a screwdriver.
No.
Slotin, you know that this thing killed a man. You are not the protagonist of an action movie. You do not have plot armor. In May 1946, Slotin was demonstrating his experiment to a colleague who was set to take over his role at Los Alamos. 6 other people were in the lab, including a photographer. And during the demo, the screwdriver finally slipped, completely encasing the core and triggering a burst of radiation. Slotin managed to knock the hemisphere off within seconds, but the damage was done. After removing the top hemisphere, he said, "Well, that does it." He died 9 days later from radiation sickness. Across these 2 accidents, 10 people were exposed to radiation from the demon core, but only 2 died as a direct.
What? Only 2 died? Wait, isn't it crazy how other guy had weeks to live? This guy only got 9 days to live? But how did the rest of them survive?
Result, which might sound like a bit of a miracle. However, a lot of that just comes down to how quickly your exposure drops the further you are from a radiation source. It follows an inverse square law, meaning that as the distance doubles, the amount of radiation is reduced by 1/4. But in the grand scheme of radiation doses, distance isn't the only thing you have to worry about. Lethality also depends on the type of radiation your body is absorbing. The type that plutonium emits when it's just sitting around is, in large part, alpha radiation. These particles are essentially helium nuclei consisting of 2 neutrons and 2 protons. They are large and slow and can be stopped by something as flimsy as a sheet of paper. Now, if they manage to get inside you, alpha particles will wreak absolute havoc on your bodily tissues, so don't go to places where there might be plutonium dust hanging around. But when the demon core went supercritical, it produced 2 other types of radiation, both super high energy particles of light, better known as gamma rays, and super high energy neutrons. Both are way harder to block. Harry Daglian received an estimated 200 rads of neutron radiation and 100 rads of gamma radiation, while Louis Slotin received an estimated 1,000 rads of neutron radiation and 114 rads of gamma radiation. To put those numbers in perspective, if you were getting a CT scan of your chest, your thyroid would absorb about 1 rad of X-ray radiation. Now, technically, these numbers don't tell the whole story about just how bad these guys had it, because human tissues don't respond to each kind of radiation the same way. For example, neutron radiation can be anywhere between 5 to 10 times more damaging than gamma rays. But we'll stick with what we've got here because we can compare them to what the 8 survivors absorbed and what side effects they encountered after the accidents. 2 men in the room with Slotin experienced some mild symptoms, including Al Graves, who was effectively standing right behind Slotin when it all went down. That meant Slotin's body shielded him from most of the blast. Still, Graves received an estimated 166 rads of neutron radiation and 26 rads of gamma. He was hospitalized for over 2 weeks and ended up losing the hair on the left side of his head. Yep, the side that was not blocked by Slotin's body. None of the other men had any immediate symptoms. Due to the extra distance from the demon core, they received doses ranging from 7 to 51 rads of neutron radiation and 0.1 to 11 rads of gamma radiation. But that doesn't mean they were spared from all negative health effects. 2 of the men, including the security guard from Daglian's accident, eventually died from leukemia. While doctors couldn't prove a causal relationship between the radiation and the cancer, they did conclude it was likely. Another 2 men died from health problems that the accident may have caused, but the evidence was less definitive. 1 man was killed in action in the Korean War, so whether or not he would have manifested any related symptoms is impossible to say. Another refused to participate in follow-up research, so his health effects are less well characterized, but he died in 2001 at the age of 81. Finally, Raymer Schreiber went on to build a new, safer facility at Los Alamos for handling plutonium. He designed it so that handlers and their radioactive experiments were at least a quarter-mile apart.
Nice.
He died in 1998 at the age of 88. As for the demon core, it was melted down and reintegrated into the National Nuclear Stockpile. It never saw battle, but it still managed to earn—
Wait, you can melt it down without getting any effects? How does that work? They were able to melt it down. The only reason it activated or reacted was because it fell? Is it like the effect, like how they were saying with the explosives when it comes to nuclear attacks and stuff like that? It just being like the effect of a hit or something hard that gets to it. Also, or is it just like, I don't know, I'm just trying to understand it now. Radiation does this thing where it can only come into contact with matter after traveling through other matter. That's why the man lost his hair on the opposite side of his head. Yeah, it needs some things to become truly dangerous. Okay, impact! It needs impact!
earn a place in history as one of the most infamous pieces of metal. And it's a pretty unforgettable reminder that lab safety exists for a reason.
Oh, that was such a good video. I did not know all this stuff about the Demon Core. It was so interesting. I hope you guys enjoyed the video. Like, share, subscribe. Bye-bye. And comment.